So today we're very glad to have Professor Laurence Perreault-Levasseur as our speaker today. And Laurence is assistant professor at the University of Montreal. And before that, she got her PhD in University of Cambridge and then did research in Stanford and CCA. I think she's also a visiting scholar now at CCA, not so far from us. Right, so today Laurence will tell us about strong lensing and machine learning. So welcome, Laurence.
Thanks. Thanks a lot for having me. It's a pleasure to be here. So thanks for the introduction. And so I'm going to talk about some recent work that we've done in strong gravitational lensing and in machine learning. And pretty small audience, so if you want, just stop me whenever you want to ask me questions, and it's okay if I don't get anywhere near the end of the talk. It's completely fine, and stop me whenever I need to stop talking. All right, so I'm going to start by just giving a brief introduction to what strong lensing is. So strong lensing is basically the formation of multiple images of some distant source due to the gravity of some intervening structure. So let's say that here we're on the Earth, like here, and there's two galaxies, one right behind the other one. So as the light of the background galaxy passes near the foreground galaxy, it gets bent. And so it comes to us from different angles. And so as a result, here on the Earth, well, this is connected somehow. Okay, right. So yeah, so it gets bent as it passes near the blue galaxy. And so like, because of that, here from the Earth, we see multiple images of the same background source. So it's a little bit like looking at a fish from the corner of a fish tank. If you ever notice, you can see multiple images of the same fish. So here's Mr. Mango, my fish, that's demonstrating this effect. So as you come to the corner of the fish tank, you can see two images of the same fish. It looks simple like this, but it took me forever to get this image. And so it makes an image that's really similar to actual images of strong lenses. So here we see two different images of the same background quasar in blue because of the gravity of the orange galaxy that's in the foreground. So here's another example of a strong lens. So here, everything we see is a galaxy, but then there's this, the contrast is not really great. But so there's a blue galaxy that's being like really wrapped around the foreground orange galaxy. And because of the gravity of the foreground orange galaxy, and it makes those arcs. And those arcs are really a common feature of strong lensing. And that's because of the geometry of the lens. So you can actually reproduce an effect like that at home with candle and a wine glass. So if you look at the flame of the candle through the foot of the wine glass, you see that as they become almost perfectly aligned, the image of the flame of the candle wraps around the foot of the wine glass, and it produces images that are really similar to strong lensing images that we see in the sky. So in this analogy, the background galaxy that's getting deformed is the flame of the candle, and the foreground galaxy that's doing the lensing is the foot of the wine glass. So that's a pretty cool effect. But like beyond just like being an excuse for drinking more wine, it's also a really good probe to do a lot of super interesting science. So the first thing we can use this for is to study the background source. And that's because lensing magnifies the images. So we can use it basically like a cosmic telescope to study very distant galaxies, very young galaxies in the universe that would be otherwise below our resolution or sensitivity limit. Another thing we can use it for is to study the foot of the wine glass or the foreground lens. And that's because the deflection of the light is due only to the gravity of the matter in the lensing galaxy. So we can use that to map out how mass is distributed in lensing galaxies, regardless of if it emits light or not. So it's a really good way of mapping out the distribution of dark matter on sub-galactic scales. So the reason why this is really interesting, and that's the reason why I'm the most interested in this effect, is because we have basically pretty much constrained that on scales larger than galaxies, CDM is consistent. So the clustering of dark matter is basically consistent with a cold dark matter model. But on subgalactic scales, different models of dark matter have wildly different predictions. Specifically, if we change the temperature of dark matter to make it a warm dark matter model, it's going to change a lot the clustering of dark matter on subgalactic scales. And so there's going to be a lot less substructure, like subhalos that are going to be predicted on those scales. So the way that lensing can help us probe these scales is based, this is my performance analogy for this. So basically, it's a little bit like looking at clouds. You know, some clouds are pretty clumpy and some clouds are really smooth. And then if we measure something about their clumpiness, we can know about their temperature. So we can do the same thing with dark matter, basically. By measuring its clumpiness on sub-galactic scales, we can know something about the temperature of dark matter. So yeah, so the way that we do that with strong lensing is basically a little bit like back to the wine glass analogy. If we have the droplet of the water on the foot of the wine glass, it's going to add an extra level of distortion to the image of the flame of the candle. And that's what allows us to infer its presence. Like, for example, here, the droplet of water doesn't emit light. The only reason why our brain knows that it's there is because it's causing an extra level of distortion in the image of the flame of the candle, basically. So, all right, and then there's one last thing that we can do with strong lensing is that we can use it to do cosmology, specifically to measure cosmological parameters like H0, and I'm going to get back to this in just a little bit. All right. But now that we know all the cool science we want to do with strong lensing, the question is like, how do we do that? Let's say I hand you an image of a strong lens, like how do I extract the science from it? So in order to be able to do that, we need to be able to do something that's called lens modeling. So we basically need to be able to infer simultaneously two sets of parameters. So the undistorted image of the background source and the distribution of mass in the foreground lens in the foot of the wine glass. And so more formally, this can be written as an inverse problem of this form where Y is a vector of noisy data. So these are like the pixels of the noisy observations. And then there's two sets of parameters from there that we want to infer. There's the source parameters. So this is a vector that contains like the pixels of the undistorted background source image. So like that's the image of the flame of the candle. And then there's this set of parameters that describe how mass is distributed in the foot of the wine glass. And those are nonlinear parameters because they go in this function L. But then the thing is that L actually is a matrix. And so because it's a matrix, the source parameters are linear parameters, but the lens parameters are nonlinear parameters. So this is a nonlinear inverse problem, but it has a set of parameters that are linear and a set of parameters that are nonlinear. And then N is a vector of additive noise. Because this is a nonlinear inverse problem, and what did I want to say? Yeah, so basically, ideally what can I do from like some data Y, we want to be able to infer both P and L. But because this function is not invertible, because it's nonlinear, we cannot do this like exactly. And then on top of it, even for X, even if it's linear, it's a non-constrained inverse problem. But on top of that, because if there's noise, there's actually some information that's been destroyed. And so the best thing we can do is that we have to basically infer the distribution of possible P's and L that have given rise to the observation that we have. So basically what we want to do is we want to infer the posterior over those parameters that describe the probability of each possible combination of foot of wine glass and flame of candle that is consistent with the data. And because it's a nonlinear problem in the P parameters, it's a really complicated function to map out. So doing this with traditional methods like MCMC is excruciatingly painful because it's multimodal and it's super, anyway, it's a mess. So, all right. So this means that it's really long to do lens modeling with traditional methods like MCMC, yes.
Can you explain the under constraint part of the linear problem?
If I had this constraint,
yeah.
So it's because, so L doesn't have to be a square matrix, for example.
Okay.
And then in that case, well, you just, it will not be invertible, right? Because it's not a square matrix. But then on top of it, there's only signal in like part of the pixels and part of the image. And so there's a lot, there's far fewer pixels that have signal than the number of pixels you have to infer. And because of that, it's a nil-post inverse problem.
Is it because we're trying to understand what a matrix is, but I mean, you only have a number?
No. Even if you know what P is and you know exactly what this L matrix is,
yeah,
it's still a nil-post inverse problem. Because there's not enough pixels in Y that have information about all the pixels in X.
I see, okay.
Well, why is that? Because maybe I would say it's the opposite, right? You start with a lens that is a source that is like almost a point source, and you distort it into many pixels. So you have many.
Yeah. So you do that for the places where you magnified, right? So you have a lot of signal there, but there's also the other pixels that's like you don't have any information over, right? Because they've been demagnified.
Yes.
There's pixels where you have less information, and because there's and most importantly, that the real answer is because there's noise, and noise always destroys information. And so the best thing you can do is to do it probabilistically, basically.
And here you don't want to assume point source, right? You also want
No, you cannot. No, you don't want to assume. Yeah. So if you have a point source, it's even like, yeah, it's It's different. So you have like, so yeah, so this is, if you have a point source, you basically have like 3 parameters. In that case, you cannot write it in this form. It's not a matrix. It becomes like, it's non-linear completely. You can also parameterize this differently, but then it's just going to be a non-linear function. Like even if you assume like a Gaussian blob or a surface profile, and you're trying to model the parameters of the surface profile in the background source, then those parameters enter non-linearly in this equation. But then there's not that many of them, so it's not a big deal. Like you could think of having like say 10-ish parameters for T and like 5-ish parameters for the source, and then that would be you'd have to run an MCMC, not like an optimizer in like 15 dimensions-ish. So that's not, I mean, it's bad, but it's doable-ish if you have a lot of compute and a lot of time. Any more questions about this? No. Oh, good. Okay, perfect. So yeah, so this means that it's long and it takes time to do lens modeling with traditional methods. So it takes about like 3-ish days to do the inference of a strong lens. But like up to now, it was not like such a big deal because we knew of like a few hundred strong lenses, and even like a couple of years ago, we knew about like a couple hundred strong lenses altogether. So even if it took like a week or even 6 months to model a single lens, it was not such a big deal because there were not that many altogether. But then with LSST and Euclid now that's already finding lenses, and with the Mormon Space Telescope, we're going to be finding like a couple 100,000 strong lenses. Like just LSST alone is going to find about 170,000 new strong lenses. So this is like, yes. Oh, sorry. It's super exciting because that's going to give us a lot of statistical power to do a lot of cool science with strong lensing, specifically like constraining the temperature of dark matter. But then the thing is like it's going to be really hard to do all the modeling. Yes.
Yeah. So for that 3 days figure,
Yeah.
How do you actually do the modeling? Because you said MCMC is painful.
Yeah.
And I'm trying to figure out if
It's
you
like
did
3
that-
days of a person time and 3 days of compute actually. So like just have to start your chain and just like let it go. Like you start an optimizer at first because you just need to land in the right place. You start an optimizer and then it goes to the wrong place. So you go back and then you're like, well, this was not the right solution. So start again. And then you just keep on going like that. And it's very long.
So like 100 times more compute would not really make it 3 days.
Well, so like for 170,000 lenses, like 3 days, and this is a really simple, like 5 parameter lens model, right? This is the first order of magnitude approximation. You cannot do any precision science with that. Like it's a really simple like SIE profile. It's like very, very simple. So if you want to do anything more fancy, it's like a lot more. So I have spent 2 million CPU hours analyzing a single lens. And a year of my time. So it was very long. So yeah, so like even if it's just like 3 days to do the simplest possible thing, it's gonna take 1,400 years. So even if you just spread it among like 100 grad students, it's still gonna take 14 years. If they don't sleep or have weekends. So clearly, I mean, this is just like not the way to go. So this seems like an unsolvable problem. But actually, a couple of years ago, we showed that there's a really easy fix to this. So we can just do machine learning, train a super simple CNN, and then we can get pretty accurate like model parameters for those parameters. So these are the parameters that describe how mass is distributed in the lensing galaxy in the foot of the white glass. So the prediction of the neural network is on the y-axis, the ground truth is on the x-axis, and it does a pretty good job. But then the main point is that this is 10 million times faster than with traditional methods. And so instead of taking like 1,400 years, it would take half an hour on a laptop. So this is pretty great. But then, since then we've done like a lot of different works on different aspects of this problem. So in particular, I said we're interested in the background source too. So basically like we want to go from like this lens image and see if we can reconstruct the undistorted image of the background source. So we already kind of talked about it a little bit, but like, let's say that I know what the lens parameters are. This is like the form that this inverse problem has. So if I know what the source is, like what the pixel of the source are, I can write the lensing matrix and then I can get the distorted image. So if I want to invert this and I know what the lens parameters are and the covariance of the noise, I can just write like what is the maximum at maximum a posteriori estimate, which is just written like that. But then, like I said, this is an under constraint problem. So in order to regularize it, we need to have a prior over background source pixels. And so if we add the prior, that's where it goes. And this is what the answer is. So if we do linear inversion like this, this is what we get. So this is not perfect, right? There's a lot of noise that leaks through the reconstruction. And the reason for that is because like we had to keep the problem tractable. This was like, let's say there's 100 by 100 pixels in my background source. That's like a 10,000 dimensional inverse problem. So I have to have something analytical to be able to invert it. So I need to have a Gaussian prior, basically. So what that does is that it constrains the 2-point correlation function of the background source, and that's it. So, and that's why like this allows noise to leak through in the reconstruction. So it's basically just ensuring that it's smooth, but then it's not going to do much more for you.
So here you
Yes.
assume you already know L.
Yes, you assume that you know L. Exactly.
So you have some model for what L is.
Yes.
How reasonable is that?
I'm gonna get to that in just a second. Well, like we just showed that you can do it with the neural network, right?
But even the neural network.
The neural network did not know anything
about.
about the source. What?
Okay.
The neural network didn't know anything about the source. It was just, I just show it an image and it predicts the parameters. It just marginalizes over the source. So you could say, you could think, okay, well, so I'm gonna have a neural network that gives me the starting point for my MCMC chain, and I can avoid all the pain, just land in the thing that has all the mass in my posterior. And starts.
Sorry, I guess that was, so you have a model for the lens. But in principle, there's some complicated 3D distribution of matter, and so the lens is not, I don't.
Yeah, this is assuming a simple parameterization.
And
But it
that's-
turns out that like most of so there's a lot of selection effects here. So the lenses that we do see are lenses that are very massive because they make big Einstein rings, and the galaxies that are very massive, they tend to be like big giant ellipticals, so they're simpler. But then it's not a perfect model. Like I agree 100%. It's not a perfect model. It's a terrible parameterization actually. And so there's a lot of people that go and they go fishing and think, oh, what about if I add this extra parameter to make it slightly more complex? Is it going to be a bit less biased? And it's a really complicated fishing expedition. So yes, but yes, it's a difficult problem. But yeah, I'm going to talk about how to make it more complex. So yeah, let's just yes.
To talk about how the properties of the noise affect this.
Yes, I'm assuming Gaussian noise. This is towards the end of my talk. If I ever get there, I'll talk about what to do with non-Gaussian noise. Okay, so all right. Yes, so the model, so we just trained a machine learning model to do this, and like the way we went about this is that we wanted to have, we thought about this in a meta learning kind of way. So we thought we're going to train this model that's going to learn the process of optimization of the likelihood in parameter space for a class of likelihoods. So it's basically going to take, like it's going to be a recurrent model that learns the path that you have to take in parameter space, like in pixel space, to land at the right place from some like initialization for a class of different likelihoods. So the way that works, because it learns a path, it's a recurrent model. And so at every step of the recursion, what it does is that it outputs its best guess. It outputs its best guess for what the background source is, like along the path that you go for, like your optimization. You pass that to your forward models. That's like the lens matrix. You produce a lens image, and then you put that in your likelihood, and then you differentiate it with respect to the pixels of the unlensed image. So that's like the parameters that you want to reconstruct. Then you pass this back into the machine learning model that outputs the next step, like something. It works a little bit like gradient descent, except that it runs like this class of particles at the same time. And then yes, and then at the end during training, you show it where it should have ended up in parameter space, and that's how it can learn like this optimization. So let's see how it does on the same example that I showed before. So here we have like the lens image. This is what we want to reconstruct. This is the same linear inverse reconstruction that I showed before, and this is the output of the neural network. So clearly, like it does a lot better. It fixes all those problems with noise making. And then to quantify how much better it does, we can look at the 2-point collection function, like the coherence spectrum between the reconstruction and the ground truth. And this is what we get. So in blue is the machine learning model, and in red is the linear inversion problem. So on all scales, it does better. And so this is really interesting because like up to that point, we were interested in this because of speed. But this was the first point where we saw, oh, we can actually do better than our state-of-the-art methods with machine learning compared to what we can do with traditional methods. And the reason for this is the prior, because with like the traditional methods, we had to use a simplistic prior that was a really poor representation of what we know about galaxies. But the machine learning model can learn implicitly a much more complex prior for what a galaxy should look like through its training data. And that's what allows it to do better than the traditional method. And so here, yes.
What about the traditional methods for
Yes.
denoise denoising because adding some sparsity
So I'm assuming that I know the noise covariance matrix. Right? These are all simulations, right? So I know
Right,
the
but
noise
if
matrix.
you assume, if you assume the covariance matrix, that's a Gaussian, that's a L2 or some.
Yeah, so there's the noise covariance matrix, but there's also the prior covariance matrix, right? So these are two different things.
Right, but what about adding L1 or prior to the optimization to make it like more sparse?
Yeah, you could do that. There's a lot of people who do a lot of different things. People think about like wavelets and like that sort of stuff.
Yeah,
There's a lot
like
of
how
different
much
like ways,
is-
but like in the end, like there's always a lot of fine tuning.
Oh,
It's like you have to like work really hard for a single lens to make it work. You have to look at to what scale of wavelets you need to go, how you cut, and like so there's a lot of like different things that are involved in this, and it's kind of a bit hand wavy. People have looked at like tessellations with like pixels of different sizes. So where you have a lot of magnification, you need like smaller pixels. Where you have very little magnification, you need bigger pixels. But then it's really like ill-defined if you want to actually do like in MCMC, because every time you propose a lens, your parameterization for the background source changes. So how do you compare the models? It's not like it's a different model, so it's not super well defined, and it doesn't really work that well either. So this is just all automated, right? Like I've learned how to optimize for like all lenses, because I've learned the process optimization of the likelihoods for all those things. And then we can look at so one criticism of this is like, oh, well, this is going to do terrible when you're out of distribution. Your background sources are like low redshift galaxies, but high redshift galaxies, they look nothing like low redshift galaxies. And so this is not going to work. So you can look at how well it does on out of distribution data. So to pick something that's really out of distribution, we look at text, which looks nothing like a galaxy, to see how if it broke, just to test if it broke, right? And so we produce like a lens image of text with noise. And so this is the linear inversion reconstruction like this, and then this is the machine learning reconstruction. So first of all, it doesn't break, so it's pretty good, and it still manages to do better than the linear inversion because it doesn't have all that noise. It doesn't show that much here because the contrast is not that good, but there's a lot of noise like that leaks through all over the reconstruction, and then so it's like it's less. The resolution is much more coherent across all the pixels in the background source, even if it's completely out of distribution. And then, like you guys like very wisely pointed out, I assume here that I know exactly what the matrix L is, but in practice, I'm going to be using like a neural network to estimate how or like an MCMC to estimate how the mass of the galaxy is distributed. So I'm never going to know what is the true L like out there. So one thing you can do is you can say, well, can I test this method when my physical model is slightly misspecified, basically. And so you can do that. So the way that we went about testing that is that we did an MCMC like on the lens parameters, but then at every step of the MCMC, you propose new parameters, and then you need to do the background source reconstruction to like know what the likelihood is. And so you can replace that linear, that step. It's usually a linear inversion method, but you can replace that by the RM, by the machine learning model that I just showed. And so if you like with just the linear inversion method, you get the red contours. And if you replace that linear inversion by the machine learning model, then you get the black contours. So every point on that step is like a slightly misspecified model. And so first, it doesn't break, it doesn't like go completely crazy. And but second, like you can also, if you have a better source reconstruction, you can also manage to get better, tighter constraints on how mass is distributed in the lensing galaxy. So this is not just about like the source science, it's also about doing better inference on what the distribution of mass is in the lensing galaxy. Okay, any questions about this? Yes.
So why did it work better even in the case with presumably the prior doesn't look anything, I mean, for text, for example, where the prior.
Well, maybe it's like really a low level, like sort of like structure kind of like thing that's important, right? Like
There's something similar between text and.
Yeah, so and whatever is similar is the thing that is important here. So like I don't have a really great intuition, but it's probably like, you know, you could think about, well, why is it that like large language models transfer so well on new tasks without even being trained? They just like zero shot learning works. Well, it's because there's a lot of common things that are like, there's a lot of the higher order correlations that we're not capturing. It's like a 2-point correlation function basically that the neural network can capture, and that is useful to do that reconstruction in that case.
I think it might also be related to still the sparsity in some bases.
Yeah.
I mean, at least
that is a very important fact too. And there's a lot of things where like a lot of the information that's missing is like texture information, which also relates to that. And so that gets filled in a way that it doesn't really impact like the overall structure, but it really helps like constraining like making it well-defined, basically.
Have you tested it on like a background source that looks very diffuse and spread out?
Yeah.
Does it work worse?
No, it works, but this is not what we're doing anymore, so if I ever get there, I'll show you what we
I
do
mean, I
now.
guess if you test a Gaussian noise as the input, that will be hard.
Yeah, that's gonna do, I think that's gonna do really poorly, but it's much better constrained by the data. So like if you're in the regime where you have like super high signal to noise, then the likelihood is gonna have a lot of information. So I'm suspecting that this is gonna still do pretty good. Because there's signal in every pixel in that case.
Yeah, but I mean, what if in the test, you have some source which are actually Gaussian noise?
Yeah, exactly. But
Like
so yeah, so the signal where it comes from. So if you have just pure noise, right? The signal comes from correlations in pixels, right? Because one pixel gets mapped to multiple places. So that's what the signal is. So that's what is the physical process that like the neural network is trying to learn. If it's learning like the actual like causal process, that's causing like the data generative process basically. So if it's learning that properly, it's going to be able to do it. And when you have Gaussian noise, you have information in all the pixels, so you can check basically. So it's an easier problem than having just a galaxy that gives you like a lot of black pixels, so you don't know if they're mapped to the same thing because they're all black, because they're also can't be black. So that there's a lot of information that's lost in that case. Yeah, right. So this is in the case where the lensing matrix like is super simple because it's a single galaxy, can be parameterized by like a handful of parameters. But then in reality, galaxies are a lot more complex than that. It's like very messy. So we basically need a much more flexible parameterization for what lensing galaxies look like. And so one thing we can think of doing is saying, well, we're going to have a pixelated density in 2D that's been predicted down like in 2D. And that's going to be my parameterization for my lensing galaxy as well. So this is really difficult with just show methods because these are nonlinear parameters, and writing down the prior on those parameters is like impossible. It's very hard. And so, but then with the method that I just showed, you could think of like having two RMs, two machine learning models that work together to optimize the same likelihood. So the way it works is a little bit like that. So the first RM is the one I just showed that just reconstructs the undistorted image of the background source. And then the second one, its job is to reconstruct the the pixelated image of the density projected down in 2D, like the density in the foot of the wine glass. And then they work together because they share the same forward model to produce a simulation. And they also share the same likelihood, but they each try to optimize that likelihood with respect to their own set of parameters. So this one with respect to the source pixel and this one with respect to the lens pixels. And then they work together like that to optimize the likelihood. And it's trained in the same way. So this is work that's been done by my student, Alex Adam. So he's used like for background sources, he's used real images of galaxies, and for lensing galaxies, you need the density, right? So you cannot use like images because images doesn't have mass, but so you can use simulation. So he's used galaxies from the LSST TNG simulation. Yes.
So if there's a supernova that goes off in the source,
Yeah.
then the images that you see in principle look different because of time delays and so on.
Yeah.
So is there like a pre-filtering step that gets rid of, how do you handle it?
So these are not like time varying sources, but
Okay. But would you be able to tell them? I mean, because
if there's a background quasar, it's time varying. Yeah, so that's part of it. You can just, it's part of the lens model. I'm going to talk about that in a little bit.
On the scheme of the previous slide, yeah, you have kind of two loops simultaneously, right? So do you have any special measures to avoid some spurious
Yeah.
feedback?
Yeah. So this is a completely multimodal problem. Like for example, I could have no mass in the lens and just a ring galaxy.
Yeah.
And that's a perfect solution.
Right.
But so the thing is, because like at the end of the day, you show this method like where it should end up in parameter space, it learns the path it needs to take in parameter space to like, it's not just purely, it's not an optimizer, it's really a meta learner that learns the path of optimization to get to the right place. So that's how it avoids it. So we were actually really worried about that. And then it just turns out that it doesn't happen. Like it always converges to something that's like not like a suboptimal minima in the likelihood. So yes, but it's a really
based on the
valuable.
prior for the source. image.
Yes, yeah, prior and for the lensing galaxy, basically. Now it's learning it implicitly from the LSST TNG data. Because that's what we're using for training. And so this is an example of reconstruction. So like, yeah, so the contrast is not super good, but like the the mass is like not super asymmetric in the lens galaxy, so that would be super hard because it's a really nonlinear problem. Having two lenses like that both influence the image is really hard to model with traditional methods. And so this would be possible, but extremely difficult to do with traditional methods. And then these are more examples of more complex mass distributions where the arm, so this is the ground truth for the source, this is the reconstruction for the source, and this is actually like a spiral galaxy, but it doesn't show. And this is like the ground truth for the mass profile in the lens, and this is the reconstruction. So we see that it manages to reconstruct like very complex lens distributions. And like I would show a comparison to like traditional methods, but I can't because I cannot get the traditional method to converge on any of those things. So this is something that would be absolutely impossible to do with traditional methods. So yes, all right. So this is really like giving us like a path towards like doing science that we were not able to do prior to machine learning. Is there any questions about this? Yes.
Yeah, so it seems it's very difficult to recover the small scale structures of the.
Yeah, because there's no signal over those scales, basically.
Okay, so that's something basically physically.
Yeah, so you can only, so you see like in the, like when you have a lens image, you only have sensitivity in the places where you have signal, right? So that's the only place where you're going to be able to reconstruct. So if the subhalo had been like here, it would have been much harder to reconstruct because there would have been no signal, like there's no trace that it's there, basically. So yeah, so that's why like a lot of those subhalos, you cannot reconstruct them because they're not on top of the lens images. Like you can reconstruct the one that are really influenced, like this one here really moves this image a lot. But like, for example, this lens here that has just like two, like this doubly image, all the subhalos that are here that are not close to the images, they're not constrained, basically. Yes. All right, there's a lot of questions at the same time. Yes.
Your training set was for individual galaxies for the source?
Yeah, and there's the galaxies for the lens.
But if they're high enough redshift, do you ever worry about having interacting galaxies?
Yeah, you could do that too. You can do that, but that's not something we did. We didn't do double plane lensing.
If you applied this blindly, not knowing what the source was, and it turned out to be an interacting galaxy, would you know right away that the image you've gotten is not reasonable?
That's a really good question, actually. So typically, if you have like multiple bands, it's pretty easy to tell when you have two sources at different redshifts because, well, it's really hard. Like if they're at different redshift, very rarely do they land really on top of each other. But then you can tell that they're at different redshift because their intensity is different in different bands. So because they're at different redshifts.
More thinking about merging galaxies, same redshift.
That would just be a more complex galaxy. Yeah, so you can have like, you can do like two galaxies in the background source. You can definitely do that. The same way that like you could do text. So.
But in principle, that should be represented in your training data, right?
Yeah, exactly.
Galaxy
Yeah, yes, exactly. Yes.
So following up on the point that Siha made, in print, so there's this, I don't remember the name, but it's like Bayesian machine learning or whatever. So
Yeah.
can you get confidence maps of this?
Yeah, so this is my next point, excellent segue. So these are point estimates. If you want to do science, you want this, you want uncertainties. This is not what you want, right? So like the point that I've been trying to make so far is really that like machine learning is going to be an essential part of our inference pipelines in like the next generation of science series, at least for like strong ones. Like, so if you want to use machine learning to do science, we need to like think of it as like this statistical model that we're using to do inference. And so we want to have access to uncertainties. And so that has motivated us into looking into like ways of quantifying uncertainties with machine learning. So the first thing that we've been thinking about was with Bayesian neural networks. Oh yeah. So Bayesian neural networks, they were super promising and say, well, there's this method, you can just like write neural networks in a fully Bayesian framework and you're going to get uncertainty. It's going to be super magic. But in fact, in practice, so basically the way that the Bayesian neural networks work is that instead of having your weights being fixed deterministic values, they are probability distributions. So every time that you put the same example through the neural network, you just draw a different sample from those distributions. So it's going to, every time it's going to give you a different output and you can marginalize over those weights and build a distribution for an output like that. But in practice, they're really hard to train for like very deep networks. And so you cannot gain like all the expressivity power that you would get with a deep neural network. So in practice, the way that people train those is using something that's called variational inference, where instead of letting those distributions like being free form, they just assume a super simple shape of distribution and they just fit the parameters of these distribution like by minimizing the KL language. So they try to make those simple distributions be as close as possible to like the free form, potentially extremely complex distribution. And then this way you can train super deep networks and it works pretty well. So this is an example of this. done on strong lensing. So this is like, so now your output is going to be a distribution. So for every parameter here, I'm plotting the 1 sigma confidence interval. And these are examples of like marginal posteriors over lens parameters for this. So this is a real ALMA data now. And so I'm comparing in black is the marginal posterior over these parameters with sample within MCMC. And in red is from the neural network. So we see that like it's accurate because it's like, it's always like correct. So we can check the calibration, but then it's a little bit broader because there's an extra uncertainty that comes from like the neural network architecture itself. So that's why it's a bit broader. So if you're willing to train a bit of like precision, but not accuracy, then this is extremely fast. And if this is broad, you can get good calibration. So yeah, this is my like sort of bullet point of like the advantages. So first of all, it's amortized, so it's really, really fast. So in this case, because I'm sampling in its anthropometric data, it's actually 1 billion times faster than with traditional methods. And then another thing that's like really good is that it allows you to marginalize implicitly over like nuisance parameters that you're not interested in. Like for example, here I was not interested in the background source. I didn't have to model it, it just marginalized over it and gave me like the uncertainties. The caveat is that because we have to assume this variational distribution, there's no guarantee that it's complex enough to really like map the true full distribution of the weights. And there's no way I can quantify how close I am. So I could think that I'm doing great, but actually I'm not. And there's a lot of problems, like for example, like these examples for like really high dimensional like inference for like CMB, like foreground removal, or if you're trying to remove like remove noise from like an RF spectrometer, you cannot get good coverage basically over those posterior because your variational distribution is not complex enough. And so because of this lack of guarantee, if it's really important to be doing like precision science and actually have extremely accurate posteriors, this is really not the best method to go forward. So that has motivated us to look towards different methods, for example, simulation-based inference. So do you guys know what simulation-based inference is? Do you need to go over this? Yes? Okay, all right. So simulation-based inference, so the way that, so this is work that's been done by Warren Legan, who's also a student in my group. So the way that it works is, okay, so it just as before, we have some parameters that we want to infer. So these are, say, the parameters that describe how the mass is distributed in the lensing galaxy. So I sample those, I pass that through my simulator, I make a mock image of a strong lens. Then I use that, I train my CNN to get a point estimator. That's just like before, right? So this is my point estimator of my lens parameter. But this is like potentially a very good compressed statistics for this parameter. Like it potentially has a lot of information about this parameter that I'm trying to estimate because that's exactly what it's been trained to do. So once my CNN is trained, what I can do is I can get a bunch of examples of those parameters, pass them through my simulator, generate a bunch of lens images, and then pass them through my trained CNN to get all those compressed statistics that correspond to them. And then when I have those two sets of like my parameters I want to estimate and my compressed statistics, I can model the joint distribution between the two. And then once I have that joint distribution, if I have a real observation, I can pass it through my CNN, get the compressed statistics, and then basically use the fact that I know the joint distribution to get the posterior. And so this is a really it's super similar to ABC. This is a really well-defined statistical framework. And it comes with guarantees that this is going to be an accurate posterior. And then basically, the other machine learning part that we have to do is to model the joint, then we can use like neural density estimators, but it's in really low dimensions. So it's like, it doesn't come with like a lot of risks as much as like the other thing. Another thing that's like super interesting is that even if my neural network here is biased and gives me a biased point prediction, I'm still going to get an unbiased posterior. So it's going to be less precise, but it's still going to be accurate.
Is there a short way to explain why that should be the case? Because it seems like if you're in the language Bayesian statistics, it seems like if you enforce some prior in the first.
So the prior needs to be, so the prior needs to be in distribution. Like you cannot have a misspecified prior in this framework, but even if your compressed statistics is not a sufficient statistics, it's still going to give you an unbiased posterior. And if when you have a biased compressed statistics, it's like not like a sufficient statistics, but it still gives you, it changes nothing to like the way that the posterior carries through. Okay, so these are two different things, like not having the right prior and like having a bias estimator is like, it's different. All right, so this is an example of this compared like that run is done on like comparing like the posterior for a single lens between Bayesian neural networks and SBI, simulation-based inference. So like in blue, it's the Bayesian neural network, and in red is SBI. And so like Bayesian neural networks, they have like some fine-tuning parameters. If you don't tune them well, they give you bias estimates. So this is an example of the coverage plot. So you see that like, provided that we have accurate estimators and that we know our prior, this is like the best way to get accurate posteriors. So the advantages is that basically we get like the best of both worlds, right? We get like the power of machine learning to get super complex like compressed statistics. We can make like the CNN, or like we can make it transformative, we can make it as fancy as we want, but then we still have guarantees about the posterior that we get at the end. And then yeah, another thing that's like super interesting is that once we get like the posterior, we can still have access to like samples that are consistent with our observed data. And so this is really powerful if you want to do something like integrating, like if we detect a signal, we want to know where does it come from. Like if I say the temperature of dark matter is 6 eV, like then like it's 6 keV, sorry. Then like I want to know, does it come from like a single, like a few like very massive subhalo, or is it a very large population of low mass subhalos? Like I want to be able to generate samples that are consistent with my data. So that's like a really advantage. Like some of the caveats that it doesn't really work in high dimensions. So I wouldn't be able to like infer a map because I need to be able to model that joint distribution. So if I have like few compressed statistics, like this works. And then another thing that is not ideal is that if I want to keep this amortized, I need to be able to, I need to model basically, I cannot marginalize over nuisance parameters implicitly. I need to model all of them. To keep things amortized. If you're not interested in like keeping the problem amortized, then it's a different story. But if you want to keep things amortized, it's like that's you cannot marginalize implicitly. So and it requires like an accurate simulation pipeline.
So basically what you were showing here was a parameterized lens model rather than.
Yes, that's why there's like so few parameters, like there's 5 parameters, right? So it's not a pixelated lens model. Like with the pixelated lens model, this would not work. Because the joint distribution would be like, let's say there's 10,000 for the source, it would be 10,000 by 10,000. So that's a lot of parameters to fit a neural density estimator. It would not work.
Well, people are talking about diffusion models.
Yes, you can do that. Okay, so yes, so this is, okay, so I'm going to skip NRAs. So there's NRAs that allow you to marginalize implicitly. And unless somebody really wants me to talk about H0, you can do H0 as well. I'm just going to skip that. And you can do, yeah, so you can do neural ratio estimator. They allow you to marginalize implicitly over like a lot of nuisance parameters, but then you lose that interpretability of like knowing where does my signal come from because you've marginalized over those. And so like if I want to know again, like temperature of dark matter is 6 keV, does my signal, where is the signal coming from? Like how do I know if this is making sense or not? Then I have lost access to that because I've marginalized overall the whole thing. So it really looks like if we want to be able to have like some interpretability and to like be able to marginalize over a large number of nuisance parameters, we're going to have to solve the hard problem of doing high dimensional inference in a Bayesian way. And so, all right, so this is not a lot of time left, but
Oh, you have.
if you let me talk, then I can keep on talking. Yeah. So
We had a lot of questions during the talk, so you can go further.
Thank you. All right. So basically, if we go back to like the other case that we had of like high dimensional inference that worked well with the RM, the thing that made it work is because we were able to learn implicitly very complex priors from data. So we had data-driven priors. Like in the case of the RM, it was learned implicitly. But then so like inspired by like some work by François Lanus, who's done amazing work in this, and also like Yang Song, obviously, we thought, is there a way to learn explicitly this prior distribution from samples? So can I model basically like the distribution of galaxies in this super high 10-dimensional space, 10,000 dimensional space? So like, so this is like a cartoon version of this. So like I have this really high dimensional space, and every point in here is basically a galaxy. So it's like a different kind of galaxy. It could be super multimodal. Like I don't know what this manifold looks like. It could be like very complex. So there's multiple ways I could think about going about learning like a density, a distribution over those. So if I want to model the density directly, like this, I know how to do that, right? Like what I would do is I would try to find something that maximizes the likelihood of the data, basically. So I could just like minimize the KL divergence. But then the thing that's difficult in really high dimension is that it's like learning the density directly involves knowing like the normalization constant. And that involves having like global knowledge about the whole parameter space. So that's really hard to learn for a neural network. So this is not the way to go. But then the thing is that it turns out that if we want to generate samples from a distribution, if we use long event sampling, the only thing that we need to know is the score. And the score is basically the gradient of the log of the probability distribution we want to sample. And because we take this gradient, that normalization constant basically vanishes, right? And so what we're left with at the end of the day is basically a vector field that points towards the regions of high density, and it only contains information that is local about like this probability distribution. So that makes it, that's really the key that makes it much easier for a neural network to learn, the fact that it has just like local information. All right, so I don't really have time to go into like how do we get the neural network to learn this vector field, but we do it with something that's called denoising score matching. And then once you've learned that score, this is work that's been done by like my student, Alex Adams, specifically like for the galaxy. So once you learn that score, you can basically learn to sample new samples from that distribution by sampling a realization of noise and then solving a reverse time stochastic differential equation to get a realistic sample from your distribution. So in this case, it's a sample of a galaxy. So there's math behind that, but I don't have time to go into the details. But basically, you can learn, if you have like a bunch of samples of galaxies, you can learn the score. And once you know the score of the distribution, you can generate new samples. So my postdoc, Connor Stone, he spent a lot of efforts like generating this great data set of low redshift galaxies that are really high resolution. It's called the probes data set. And then he's trained a diffusion model, a score-based diffusion model on those. So there's a lot of those galaxies that are not, there's about half of those that are not real and half of those that are real. And I do not know which one is which. If you want to have fun, you can go here and generate a lot of fake galaxies as well. But yeah, so I would not be able to tell you which one is which. Okay, so now we have a way of learning the score of our prior. And then we can generate new samples from this distribution. But what we want to sample is not the prior, it's the posterior, right? So, but then I can use Bayes' theorem to decompose this into the score of the likelihood and the score of the prior, plus like the score of the constant normalization constant, but the normalization constant vanishes, this is the score, right? So the score of the prior, I've already learned it, so we're good. The only thing we're missing is the score of the likelihood. So this is actually intractable. But because in the case of source reconstruction, it's a linear inverse problem, and I have Gaussian noise, I can actually write down a fairly good approximation for this in a way that allows me to basically evaluate. In a way that allows me to evaluate this at finite temperature and at zero temperature. So I can generate samples from my posterior. So this is an example of what we get. So this is the background galaxy, and this is like the model. So this is an example of the posterior samples as a function of how much noise I add to my observation. So in the case where there is very little noise, there's a lot of constraining power in the likelihood because there's a lot of information in the likelihood. So the different posterior samples are going to be very consistent with each other because it's very, very constraining. But then as I add more and more noise, there's going to be a lot more variability between different samples. And in particular, in lensing, the center of the background galaxy, like the thing that's aligned with the lens, gets really highly magnified. So there's a lot more constraining power there. So across the different samples, like the center of the background galaxy remains like fairly consistent, but then the outskirts have less information. They get like buried under noise as we add more noise. So then its information comes on the prior that comes and fills in information that's missing. And we can see how this interpolates as we add more and more noise. There's like here, like all the outskirts get filled in by like galaxy information from the galaxy prior, basically, up to the point where there is only noise in the observation, and then there's no constraining power in the likelihood. So we just get a random sample from the prior, basically. And then if we were going to average, we wouldn't see anything that's consistent in the image. So we can do things like quantifying uncertainties over like our reconstructions. We can, if there's like something that we're reconstructing in the sample, we can say with what significance we detect like whatever satellite galaxy or something, because we detected like X number of sigmas or something. Across, like by looking at fractions between different samples. So now we can go and play the same game of looking at like, how does it do out of distribution? And so we looked at like a 7. So we asked DALI to generate a 7 in the shape of a galaxy. We wanted to have 42, but it didn't work really well at the time. So we settled for 7. So this is like the ground truth. This is the model. So this is as a function of the level of noise. So we see again, when there's almost no noise in the image, there's a lot of concerning power in the likelihood. So we get samples that are really consistent with each other. But then as we add more and more noise, there's a lot more information from the prior, which is a galaxy prior, that comes and fills in the missing information. And so we see, and then we see that the things that are consistently reconstructed across the different images are the places in the likelihood where there's more information, because this is the place that's like highly magnified. And then again, in the case where there's like no information in the likelihood, it's just noise, and we just get random samples from galaxies, which is our prior. So it's doing exactly what we expect this to be doing. Is there any question about this? No? Okay, all right. So these are samples. They kind of make roughly what I expect them to be making, but like, how do I know if they're like actually samples from my posterior or like some slightly different distribution? So the way that we typically go about testing that is with something that's called the coverage test. So basically, like for a confidence interval, like the coverage of the interval is the number of times that like the ground truth falls within that interval over like multiple experiments. So let's say I'm looking at like the 68% confidence interval. I would like the ground truth to fall within that interval 68% of the time, right? So I would like the two to be equal for my posterior to be well calibrated. So it's difficult to look at it, and that would have to be true for like every like posterior, like any biweekly volume that I'm looking at. This could be like true in high dimensions as well. So to do those coverage tests, it's difficult to look at the highest posterior density critical region. So that's the place that has like the minimal like area in parameter space, basically, like the minimal like volume in parameter space that has like the highest density. So this is like the way most of those tests are run. But there's a lot of downsides with doing a coverage test like that. Like, first of all, you need to be able to evaluate the density. But then if you just have access to these 4 models, you don't know what the density is. You just have samples, right? So that is not super easy. And it's also really high in high dimensions. Like if I have an image, it's really hard to go and evaluate the density in like 10,000 dimensions and say something like meaningful, because you would need so many samples to be able to do that. And then another thing is that this is a necessary condition for calibration, passing this test, like the highest density region test, but it's not a sufficient condition. Like for example, if I have a symmetric distribution like this, and I'm always predicting like to the right of the peak, I could completely pass this test, but I'm really biased because I'm always predicting to the right. So this is not an accurate posterior. So there's a lot of cases where this would not detect that you're not calibrating. So what we've done with my postdoc is that we came up with a new way of designing confidence intervals, basically, but not intervals like critical regions, because it could be in high dimension. That does not rely on evaluating density, but just relies on like defining those regions differently using a random point, basically. And yeah, and it scales to high dimensions because it only relies on being able to evaluate the distance in between different points, and you can define any distance. It could be the L1 distance, could be the L2 distance, but it's something that scales really easily to high dimensions because the distance is really easy to evaluate. And then the other thing that we've done is that we've proved sufficient and necessary condition for calibration. So if you pass this test, you're guaranteed to be calibrated. And so this is a package that's pip installable, so you can go play with it. It's super simple. So this is like more in details how this works. But I'm happy to answer questions about this if you want to know more about specifically how it works, but I can just skip this.
Are there assumptions about multimodality?
Yeah, it works for multimodality too. There's no assumptions about multimodality.
Because
You just have to be able to generate a random point from anywhere where you have coverage in parameter, where you're like, yeah, when you have coverage, when you have support in parameter space.
so it's because of step 4 that it works on multimodality.
No, so step 4 is like, so it's, okay, I can explain what this is. So this is just calculating the expected, so you just have to repeat it over multiple distributions. But so, yeah, do you want me to, I can explain how this works, or I can just move on to more things. I mean, if you're interested, I can explain to you how this works after maybe. Yeah, and then we can look at like how we are doing with the galaxies. So I talked about how like the score of the likelihood, there's an approximation that needs to go in there. So if we're very naive on how we evaluate it, we find that like the galaxies that we recovered, they're biased. But then if we're careful about the approximation we make, it's still an approximation, but we're more careful about how we include like the forward model in there, then we find that we have well calibrated reconstructed galaxies. So all right, so now we're in really great shape to go and make groundbreaking discoveries with machine learning in strong lensing. But then this all assumed Gaussian noise. And in reality, noise is not Gaussian. So these are real examples of noise from HST and JWST. So there's a lot of cosmic rays, but like even like JWST, there's like those stripes that are horizontal stripes and those like vertical stripes. And this is clearly super correlated. So the Gaussian likelihood is not going to work really well. But we can do the same thing. Like we have samples of noise where there's no signal of interest. So we can just learn a score-based model to produce more samples of just noise. So these are samples of noise from my score-based model. So this is fake noise. And then so what I could do is I could use those in my simulator to have like a realistic noise simulator to do like SBI. Or I can use this score of the noise model as my data-driven likelihood in an explicit likelihood formalism. So the way that it works, so yeah, this is the score of the noise, Q is the noise. So basically that's what I learned. So where Q is like my distribution of noise. So it's like the distribution of noise, like all the possible, it's the density of the noise in like this super high parameter space. So what we need to like realize is that distribution for noise is related to the likelihood, because if I write my noise, if I have like my data minus my model, what's left should be just noise. And that's exactly what the likelihood is. So basically what I'm learning is the score of the likelihood. So I could just go ahead and sample this with Langevin sampling the same way that I've done before, except that with the score of the likelihood here, except that the score that appears here is a score with respect to the parameters that I want to sample. But this is not the score that I learned. I learned the score with respect to the pixels of the observation. But if I have a differentiable forward model, I can just use the chain rule to write this like this in terms of the score that I know times the Jacobian of my forward model. So if I've written my model in PyTorch, for example, or in JAX, and it's like automatically differentiable, then I have this for free. So you can go and do inference on this. So this is a real example of noise, and it doesn't show really well, but there's like those like super nasty stripes. And so this is noise, and then this is an injection of a strong lens in there. So if I was going to be very naive and say, I'm assuming a Gaussian likelihood, and I was going to do the inference with traditional MCMC method, I would get the blue contours, which are clearly very biased. But if I use this, it's called the slick likelihood, this score-based likelihood, then I'm going to get unbiased inference. And so you can do the TARP test to see if you're biased or not over like multiple examples, and then you get unbiased inference, basically using this like data-driven likelihood. So yeah, so I can stop here. I have like a couple of other examples of combining score-based likelihood with score-based priors, if you want to see. It's up to you.
See whether we have questions probably.
There are more questions?
So, yeah, I mean, this is SBI, right?
This is not SBI, it's Langevin sampling. So I'm not doing SBI. I'm modeling again, I'm just doing zero temperature, like it's like pure like MATLAB basically at zero temperature to sample the parameters. So there's like 5 parameters in my lensing galaxy, and the likelihood that I'm using in my Langevin sampling algorithm is the one that I learned from my like patches of empty noise.
And so the coverage is in the lens parameters.
Yes, it's in the parameters.
Okay,
Yes.
so I guess it will still be very hard to do coverage in the source plane in the 10,000.
Yeah. But you can. So this isn't this coverage is in the source plane, right? Because it's the TARP thing. These are for the background source, like the pixelated background source reconstruction, because it scales to height, like the TARP, like the TARP test scales to high dimension because it only requires defining like the L2 distance in 10,000 dimensions, which is not that difficult or expensive to evaluate. And
Probably,
yeah,
we can conclude it.
all right, so I'm just gonna skip right to my final slide with like the cool images. We can do better than, with HST, we can do better than JWST. And let's skip this. All right. And All right, so I hope that I've convinced you that in the coming years, with like 200,000 lenses that are coming, we're going and with machine learning, we're going to be well equipped to do like groundbreaking discoveries about dark matter. And well, I didn't talk about HNOT, but dark matter. So yeah, thank you.
You didn't talk about it, not, but it remind me of the following thing, which is that when you model these lenses, there's this mass sheet degeneracy. Right?
Yes.
And so presumably it could learn some correlation between the shape of the galaxy and the actual.
Yeah, absolutely. Absolutely.
So you would be, in some sense, breaking the mass sheet degeneracy, getting an answer, but it's really because you're putting it in through believing that the simulations accurately.
Yes, absolutely.
So this might be happening for other things inside. How do I deal with this?
So doing inference always relies on being able to simulate things, right? So because even if you're doing like traditional, MCMC, you still need to like have your model that you're putting inside your likelihood to evaluate your likelihood, right? So like this is not a new problem to be able to like the need for doing simulations is not a new problem. It was always there. Right?
I agree, but
but then the thing is like the inference
you don't have the control, right? So if I'm putting some prior on the mass sheet.
Yeah, but you would put that prior like through the simulations that you're running to do this, right? And so it would be like if you have a parameter that allows like the range of like simulations to look like this, then like that's what you would put in like your simulation. So in the case where you're doing simulation-based inference, instead of like being really difficult to do the actual inference itself, like that problem's sort of been removed and it's shifted towards like just actually being able to have like an accurate simulation pipeline, which is arguably much easier and which like you needed to begin with. And also like if you have, but like right now it's so hard to do this inference with mass degeneracy that even when you're trying to break it with like additional like velocity dispersion data. So what you do is you do the mass model for the lens, and the mass model is going to have some ellipticity. It's going to have like, it has a lot, the dark matter halo has like some structure, some orientation, like it has like, even if it's very simple, it still has like some like ellipsoidal-ish structure. But then when you're doing the stars modeling, you do spherical genes modeling, that's it. You don't assume any correlation between it, except that you're using the stars to like break the mass degeneracy. So like, and that's because you cannot do any better because the likelihood is intractable. So even if you were just able to like jointly model the stellar population and the dark matter mass, it would be groundbreaking. Which you can do if you can just simulate these, which is much more tractable than trying to do the inference implicitly.
So have you done that? Was that the part you skipped?
Well, no, so we're working towards that.
Okay.
But no, so this is something that's like we're actually involved in like working. So there's these like awesome guys, they're writing this package to simulate strong lensing and all the like possible effects, like all the line of sight halos and like the multiply lensing that goes with that, and all of that with like in a way that's fully differentiable and like super modular. So if you want to include some effects and not others, if you want to have a score-based model for your background source, if you want to have some like pixelated model for the foreground lens, you can do that because it's like super modular and it's fully differentiable. And yeah, and it's probably.
But does that include we're not.
So yeah, we're not, so we're still
dynamics,
continuing on like, so we're still like improving this, so we just got a grant to actually do that part.
I
So we have a
the part
student
where
that-
you were training on illustrious, of course, in principle, you could use the stellar.
Yeah,
velocity, so-
exactly. But yeah, but you don't, so stellar population modeling is not something that's like explicitly done. If you just get like the mass from, like you get the mass in the stars, right, from illustrious, but then you still have to do like radiative transfer and you need to do like stellar population modeling, and there's a lot of assumptions that go in those that could also introduce potentially biases.
Absolutely, yeah.
So probably we have time for one last question. Then I will ask one. So what do you think will be the biggest signs in when you have like several thousands, tens of thousands of lenses?
So I think that this signal that is really like the thing that like I'm putting my money on is definitely dark matter.
So that will be the number of abundance of
Yeah, exactly. Putting constraints on the the temperature of dark matter. Because the baseline model, the signal is like so ridiculously high that it doesn't really depend that much on like so much like the specifics of grid physics. It's not something that's subtle. Like the prediction is that there is a lot of those subhalos. And if you don't see them, there's like, there's a lot of things to learn. So like not seeing something is actually really interesting in that case. And so the signal and the predicted signal is like really big. And there's like, actually, if you look at like the line of sight subhalo, there's like the signal is like 10 times stronger for like those interloper halos than the ones in the host galaxy. So it's not even like dependent on like the specific feedback that we have between like subhalos and the interaction they have with the stars, etc. Like this is not even the important part of the signal. Like it's
And
just
that's also included in
Yes.
the Lenson model.
yeah. We include that in the forward model. Exactly. Yes.
It's quick.
Yeah, very good. So subhalos are like diffuse objects, but they can have more compact perturbers like black holes.
Yes, you could.
So have you thought about incorporating black holes in your foreground or background?
So yeah, you could definitely go into more exotic models for dark matter. That's for sure.
Not for dark
but-
matter.
but
Let's
yeah,
say
in
black
general,
holes are
yes.
not dark matter.
Sure.
Only black holes.
Yes, so like right now we're just trying to find like a signal, right? Like, so like it's very simple, like the parameterization is very simple. So we're just like in the mass function of subhalos, we're just trying to find like a break or like a 2-parameter model where you're just trying to fit like the amplitude and the place and like a slope. So either like you do like an amplitude and a slope, or you do like just a break, like the temperature. And just that, even like this super simple parameterization is like groundbreaking. Because it's measuring something. And the signal is really
And then-
strong. So there's like data is definitely sensitive to the signal. It's just that we don't know how to analyze it yet. So
Okay, then let's thank again for Laurence's wonderful talk.